Welcome everybody. In this next set of videos, we're going to focus on how to work with rational expressions. So in this video, we're going to do an introduction to what rational expressions are. We're going to look at the domain and then also how to simplify them. So first, a rational expression is the quotient of two polynomials. So quotient means division. So basically we're looking at ratios here, or they look like fractions, but instead of just having a normal, let's say numerator and denominator, they're going to be polynomials. So for example, you could have something like this. Or something like this, a little bit more complicated. Even something like this, something more simple. So anything that kind of looks like a fraction but has polynomials in the numerator and or denominator is going to be a rational expression. Technically, even a fraction would still be a rational expression. 2 and 3, I know they're both constants, but they do still fall under the definition of polynomial. So you can even count something like this. But typically in this section, again, we're not going to just focus on the basic fraction stuff. We're going to really focus on things that have x's in your numerator and denominator. Now, when finding the domain here, the big thing we have to watch out for is making sure we do not divide by 0. Okay, so we must exclude any numbers that would cause dividing by 0. Okay. So for us, the big thing is going to be watching out for those denominators. You need to make sure your denominator is not 0 when you're dealing with rational expressions. So let's look at a couple of examples. Okay. Actually, maybe we can do some of these ones up here. Let's start with this one. X plus 1 over 3. This is a rational expression. And if you look at it, the denominator is 3. So see how your denominator here will never be 0, right? There's no way to turn 3 into 0 here. So because the denominator will never be 0, we have nothing to worry about in this case. So our domain in this case is going to be all real numbers. And this symbol here just means numbers. Let's do a little bit simpler one too. How about 1 over x? Now, if I look at something like this, I can see that I have an x in the denominator, and x can take on different values, so I have to be careful here. I do need to make sure my denominator is not 0. So we need the denominator to not be 0. So in this case, I need to make sure my x value is not 0. So this is the number that I'm going to exclude. So we'll go all the way from negative infinity to 0 and from 0 to positive infinity, or in set notation, all x as long as x is not equal to 0. All right, and let's look at this example right here. So again, we need to make sure your denominator is not equal to 0. So what we typically do, if you can't just figure it out, this one was pretty straightforward because it was just x, so we have to exclude 0 there, but you're going to actually want to factor or solve this. So this one is factorable. We can factor into x plus 1, x plus 1. So I want to make sure that this is not equal to 0. And what you can do is just solve it very similar to if it was equal to 0. You set each factor equal to 0 and solve, or not equal to 0 in this case. So I subtract 1 from both sides. Now I get the same answer in each case here, right? Same factor, subtract 1. So x cannot be -1. So I have one value I need to exclude here. So again, all values are okay, but x cannot be -1. And let me do one more example here, just to show you another one that's a little bit harder as well. So let's say I have 7x all over x squared minus 36. Okay. So here I want to make sure my denominator is not equal to 0. Again, for most of these, they're going to be able to factor because that's the main thing we know how to do with polynomials. If you can't factor and you do have a square, you could try using the quadratic formula as well. So that's another strategy. But again, for our purposes, these are typically going to be factorable. So this factors into x plus 6, x minus 6. I set each factor equal to 0 or not equal to 0. As long as you exclude those values in the end, you can think of it either way. And here I have two values to exclude. So my domain in this case would go from -infinity to -6, then from -6 to +6, and then from +6 to infinity. So I'm using interval notation here, and I am skipping over the -6 and the +6. If you were using set notation, you would write x such that x is not equal to 6 and x is not equal to -6. So you may have just one thing to exclude. In rare cases like the first one we saw, you may have nothing to exclude. I would say that does happen more rarely. Usually there is something to watch out for in most of our examples, or you could even have more than one. So this one has 2, but you could have 2, 3, 4, etc., depending on how complicated that problem becomes. So I also want to talk about how to simplify. And I want you to think about how you would do a fraction problem first, right? So let's say you had a basic fraction problem. Maybe I have, how about 6/9? Right? Now there's different ways to simplify. You can either think of it as dividing or canceling out common factors. So if I think about canceling out common factors, well, 6 is the same thing as 2 times 3, and 9 is the same thing as 3 times 3. And what you can see is that 3 cancels out in both cases, right? So you're basically dividing both the numerator and denominator by 3 here. And then we're able to go ahead and simplify to our final result. And we're going to use the same technique with rational expressions. So we just cancel factors in common to both the numerator and denominator. So very similar technique with rational expressions, obviously a little bit more complicated because you have x's and things, but that same basic idea that you're looking for what is in common to both the top and the bottom that we can cancel out. So let's look at a couple of examples. So here I have x cubed plus x squared over x plus 1. So when you're thinking about canceling factors, for polynomials, you really want to think about factoring first. So for most of our rational expression problems, your first step is probably going to be to factor something. So if you're kind of stuck and you don't know how to start, think about factoring and breaking it down. For this one here, I can take an x squared out of my numerator. It does have a GCF. So if I take an x squared out of x cubed, I have an x left. And if I take an x squared out of here, I have a 1 left. And then in the denominator, I also have an x plus 1. Now, this is one factor that stays together as a group. So what happens is the x plus 1 factor can cancel in both cases. And we can simplify this to just x squared. Now, I am going to warn you here with domains, with rational expressions, you really need to go back to the original problem to do your domain. So I know that the x plus 1 cancels, but because that original problem had a denominator, that is where you're looking. So you're kind of looking both at the beginning and at the end to see what was the original issue, did you create any new issues along the way with factoring, and really watching out for that. So here for our domain, Even though it cancels out, you still need to worry about this. So we still need to make sure that x plus 1 is not equal to 0. So we are going to exclude -1 from our domain, even though when we simplify, it cancels out, it doesn't matter. So just be careful when you're doing domain and range that you're also checking those original problems, that original problem when you set it up. All right, let's try another one. There we go. And again, our goal here is just to simplify. So if you're simplifying, you want to think about factoring. So your numerator can factor. X squared breaks down to x, and 5 is just 1 and 5. So to get this positive signs, you're going to use plus signs here as well. If you're not great at factoring, make sure you go back and review our videos on factoring, and then always check. So do a mental check or a physical, actually multiply everything out here and make sure you do have the original polynomial. You don't want to keep going if your factoring is wrong and waste all that time. Here, x squared minus 25 is going to factor into x plus 5, x minus 5. So you're going to see that that factor pair of x plus 5 cancels. I will warn you, make sure you only cancel factor pairs in their completeness. So for instance, here, when I rewrite this, I have x plus 1 over x minus 5. I can't just cancel the x's. Okay, I have to make sure I cancel the entire factor. So here, when you have plus or minus signs, that is one group. So I cannot cancel just x's here. I have to cancel the factors completely. So you do need to make sure that they match. So this is our final simplified problem. But again, when you're doing your domain, you have to be careful here. You do have a denominator here that's different than this one, right? So if I look at this denominator, it was x squared minus 25, which factored into x plus 5 and x minus 5. So you have two pieces here we have to watch out for. So you have to exclude -5 and then also +5. So again, you see the +5 at the end, but you have to be careful when you're doing domain. With rationals, you need to consider the entire problem. So also look at the very beginning of the problem, and again, kind of also at the end to make sure you didn't create any new issues along the way when you were simplifying. So here we have two values to exclude. So it's going to go from -infinity to -5, -5 to +5, and +5 to infinity, or in set notation, you're excluding both -5 and 5.